We're told that AI has reached state-of-the-art performance in colonoscopy polyp segmentation. But what if those numbers are lying to us? The past 5 years have seen a rapid succession of deep learning architectures, claiming record-breaking results on standard benchmarks. But when we actually audit how these models are evaluated, a different story emerges. A recent systematic review of 27 papers published between 2015 and 26 reveals that the field's progress is built on 3 structural flaws: widespread metric omissions, incompatible evaluation protocols, and a near-total absence of statistical rigor. In fact, even papers published after the 2024 Metrics Reloaded framework continue to ignore these issues, suggesting that broader methodological guidance hasn't reached this subcommunity. To understand why this matters, we need to look at what's actually being measured, how models are split, and what happens when we stress-test these claims under controlled conditions. Let's start with the metrics. The field converged around a 6-metric template introduced by ProNet in 2020. It relies heavily on mean dice and mean intersection over union. These are region overlap metrics. They measure pixel-wise agreement between the predicted mask and the ground truth. Mathematically, dice is 2 times the intersection divided by the sum of the areas. It's intuitive but clinically detached. In live endoscopy, a model's utility isn't about maximizing pixel overlap. It's about 2 things: lesion-level sensitivity, meaning you don't miss a polyp, and boundary accuracy, meaning you know exactly where the resection margin should be. Dice completely obscures both. A model can achieve a high dice score while missing 30% of the polyp tissue, or while predicting a boundary that's hundreds of pixels away from the true edge. That's why the Metrics Reloaded framework recommends pairing overlap metrics with boundary-sensitive measures like the 95th percentile Hausdorff distance, or HD95. HD95 measures the maximum distance between the predicted and true boundaries, ignoring the worst 5% of outliers. It also recommends normalized surface distance, or NSD, which scales that boundary error relative to the total surface area. When you add recall or sensitivity into the mix, you finally capture clinical safety. False negatives in screening carry the highest cost. Yet 25 out of 27 audited papers completely omit HD95. 25 out of 27 also fail to report recall. But the metric problem is only half the issue. The other half is how the data is split. The ProNet template established a fixed train test split: 1,450 images for training, with the remainder used for testing. This fixed split became the de facto standard. But if you look at the literature today, you'll find at least 5 different split protocols running in parallel. You have the original fixed split, random 80-20 partitions, K-Vassar-only splits, custom splits with additional training data, and video-based splits. These are fundamentally incompatible. When CF-Former and G-Cascade both report dice scores on the same datasets, they're using different partitions. The numerical difference attributable to split choice alone can exceed 3 percentage points. That's larger than the claimed improvement of several state-of-the-art papers. You're literally comparing apples to oranges on shared leaderboards. And then there's the statistical vacuum. 26 out of 27 papers report performance claims with 0 statistical significance testing. No p-values. No confidence intervals. No correction for multiple comparisons. In a field where claimed improvements are often measured in hundredths of a point, this isn't just sloppy reporting. It's scientifically invalid. To prove these aren't just cosmetic issues, the authors re-evaluated 5 representative models under 3 controlled protocols. First, they tested them on the original fixed split. Second, they retrained them under 3 different random 80-20 splits. Third, they pushed them out of distribution using PolypGen, a 6-center dataset that the models have never seen. The results dismantle the illusion of stable progress. Under the fixed split, region metrics hide severe boundary failures. On the ETIS dataset, one model's HD95 is nearly double that of another, a gap far larger than the 0.15 dice difference suggests. Its recall sits at 0.67, meaning it misses a third of the polyp tissue. When you switch to lesion-level detection using connected component matching, the ranking completely reshuffles. Dice rewards overlap, but lesion-level F1 rewards actual clinical utility. Did we detect each lesion without generating false alarms? Under that metric, a model that ranked 4th on dice actually leads in precision, while another that ranked 2nd on dice misses up to a third of lesions and generates the most false alarms. Then comes the split sensitivity test. Under random partitions, the models are statistically near indistinguishable. The standard deviation across seeds is between 0.005 and 0.007 dice. In some cases, the ranking between the top 2 models flips entirely depending on the random seed. A single fixed split leaderboard does not establish a robust ordering. Finally, the out-of-distribution test shows the real-world cost of benchmarking inertia. On PolypGen's 6 unseen centers, every model drops sharply in absolute terms. Dice falls to between 0.71 and 0.76. HD95 balloons to between 145 and 162 pixels. The course ranking is largely preserved, but the absolute degradation is massive. This proves that in-distribution benchmarks have become pseudo-training signals. Models are overfitting to the quirks of a few public datasets, and that fragility only surfaces when tested on truly unseen clinical environments. So what do we do about it? The authors propose the Polyp Segmentation Reporting Checklist, or PSRC. It's a 5-point standard designed to correct this path dependency. First, report HD95 alongside Dice. Whenever boundary accuracy matters for clinical tasks like lesion sizing or resection planning, HD95 is mandatory. Dice alone is insufficient. Second, report recall or sensitivity. In screening applications, false negatives are clinically worse than false positives. Recall must be a primary metric, not an optional supplement. Third, specify the split protocol precisely and justify comparability. Papers must state whether they use the ProNet fixed split, a random partition, or an official dataset split. Papers using non-standard splits must not place their numbers in columns that implicitly compare to fixed split results. Fourth, include at least one external or out-of-distribution test set from an unseen center. Results on PolypGen, BKAIGH, or private clinical data are required to support generalizability claims. Fifth, report statistical significance. Wilcoxon-Signed-Rank tests or Friedman tests over per-image score distributions are sufficient. Tabular Dice comparisons with fewer than 2 decimal places of separation should not be labeled state-of-the-art without a p-value below 0.05. This isn't just about polyp segmentation. It's a warning for the entire medical imaging community. Benchmarking protocols, rather than architectural innovation alone, dictate reported progress. When we optimize for boundary refinement using a boundary-weighted structure loss, but only evaluate with region overlap metrics, we create a fundamental asymmetry between training objectives and evaluation criteria. When we compare models across incompatible splits, we manufacture false progress. When we skip statistical testing, we mistake noise for signal. The release toolkit and the PSRC checklist provide an immediate path towards standardized, robust, and clinically accountable evaluation. If we want AI to actually assist endoscopists in real time, we need to stop measuring what's easy and start measuring what matters. Because in medical imaging, a high Dice score doesn't save lives. Accurate boundaries, reliable recall, and reproducible benchmarks do.